Hey Calculus class, today you're going to learn topic 23, related rates. So, related rate problems deal with quantities that are changing over time and that are related to each other. We will be looking for the rate of one quantity given the rate or rates of another quantity. We will assume all quantities are implicit functions of time. So that means that we will be taking the derivative of everything with respect to time or with respect to t. So let's go through some steps on how to solve related rate problems. Step 1, read the problem. I'm not kidding. You would be amazed at how many people skip this step. Step 2, get a pencil and draw a picture of what is going on. Step 3, list the information that you are given and/or label it on your picture. Label things that change with variables and things that don't change with the given numbers. Step 4, list the information that you want to find. Step 5, write an equation that relates all the quantities in your picture. You will need to remember some of your geometric formulas here. Now, this next step, it's called step 5.5 because sometimes you don't have to do this step. You may need to rewrite some of the variables in terms of the other variables. This is only if you do not have the rate of that variable, and you may have to use geometry. Step 6, differentiate the equation implicitly with respect to time. The derivative equation must contain at least two derivatives, such as this example, dv dt and dh dt. One of them you have to find. The other one is a rate that you should have been given in your given information. Step 7, plug in the given values for the variables and derivatives. This must come after differentiating. Then solve for the unknown quantity. Make sure to label your answer. Alright, so we're going to look at three different types of problems. The first type is when you have to use similar triangles. And I just want you to keep in mind that I'm going to give you examples of the three main types that you may see in calculus. But there are multiple different types of related rate problems, and I can't go through every single type you see. All right, so the Bigfoot problem. Bigfoot wanders out of the mountains and onto a city street in Seattle, weighing in at 441 fur-covered pounds and reaching a height of 8 feet. Suppose that Bigfoot walks quizzically toward a streetlight at a rate of 2 feet per second. If the light is at a height of 12 feet, at what rate is the length of Bigfoot's shadow changing when he is 6 feet from the base of the lamppost? All right, so we just read the problem. Now let's draw a picture. Pretend that this is Bigfoot. All right, so we have the lamppost, and he is walking from the base of the lamppost, so away from the lamp. We want to know the rate at which the length of his shadow is changing as he is moving away. So the given information that we have is that the height of Bigfoot is 8. Now, because the height of Bigfoot does not change over time, I can label it as the number 8 on my picture. The height of the street lamp is 12 feet, and that also does not change over time, so I label it as 12. What is changing is his distance from the base of the lamp to him himself, so I label that with the variable x. The rate that I'm given is the rate at which his distance is changing, so that means I call that dx dt. And I used x because that's what I labeled it on my picture. And equal to -2. And the reason why it's -2 is because he's walking toward a street light at a rate of 2 feet per second. So the distance between him and the street light is getting smaller. Hence, the radius is negative, or the rate is negative. So what we want to find is this length, the length of his shadow. So I'm going to label that as y. So that's what I want to find. I want to find the rate of y with respect to time when he is 6 feet away from the lamppost. So that means when x equals 6. Now you have to write an equation. So the best way to do this is you have similar triangles. So if you remember from geometry, you have this small little triangle made up of him and his shadow. And then you have the big triangle made up of the street light and the whole distance from him to his shadow tip. So when I relate it as similar triangles, I have 8 is to 12 as y is to this whole length of the triangle, x plus y. Now I'm going to go ahead and find the derivative. Notice I am not plugging in anything for x and y because those are the things that are changing. All right, so I start with my equation and I just reduce the 8/12. And I'm going to multiply across so I don't have to use the quotient rule. Distribute through and get like terms on either side of the equation. So I did some algebra first to make my life easier when I take the derivative of this equation with respect to time. So if I left it like this, I would have had to use the quotient rule and get really ugly. But by cross multiplying and simplifying, I get something much nicer to work with. So I'm going to go ahead and take the derivative of 2x with respect to time and the derivative of y with respect to time. And when I do that, I get 2 dx dt equals dy dt. Now I can plug in the stuff I have. I know what dx dt is. That was given to me, -2. I want to find dy dt. So I plug in what I have, and I simplify. So this tells me that the rate at which his shadow is changing is -4 feet per second. Notice how I labeled. And the -4 is telling me that his shadow's length is decreasing 4 feet every 1 second. All right, go ahead and pause the video and see if you can do this one on your own. All right, let's see how we did. A man 6 feet tall is walking away from a street light 20 feet high at a rate of 7.5 feet per second. What is the rate of change in the length of the man's shadow when he is 10 feet from the street light? So here's my picture. I'm going to list out my given. I have the given of the height of the man, which is 6. His height doesn't change, so I can label it as a 6 on my picture. The height of the street lamp is 20. The distance between the lamp post and the man is changing at an x distance. And I know that rate, which is dx dt, which is 7/2. And since he's walking away, that means the distance is getting larger, so his rate is positive. And what else is changing is the length of his shadow, so I'm labeling that as y. So that's what I want to find. I want to find dy dt when x equals 10. So the equation I'm going to have to write is a proportion, since I'm dealing with similar triangles. So I relate 6 is to 20 as y is to x plus y. Reduce, cross multiply, distribute, combine like terms on either side of the equation, differentiate with respect to time, plug in what I know, solve for dy dt, and you would get that his shadow is changing at a rate of 3/2 feet per second. The other type of problem that you are going to deal with is a volume or area problem. And I call this problem the wine barrel problem. Suppose the wood nymphs and satyrs are having a hot party in honor of Bacchus, and the wine is flowing freely from the bottom of a giant cone-shaped barrel, which is 12 feet deep and 6 feet in radius at the top. If the wine is disappearing at a rate of 6 cubic feet per hour, at what rate is the depth of the wine in the tank going down when the depth is 4 feet? All right, so I have my cone-shaped wine barrel with some wine in it. What I know is the height of the wine barrel, which is 12, and the barrel doesn't change height, so I can label that as 12. I also know the radius of the wine barrel, which is 6 feet, and that is not changing as well, so I can label it as a number on my picture. What I am given, the rate that I'm given, is the rate at which the volume is decreasing over time. So the volume is decreasing at a negative 6 cubic feet per hour. Now, on my picture, I do not have the height of the wine. That changes. So I label that as H. The radius of the wine itself also changes. So I label that as R. So what I'm trying to find is the rate at which the height or the depth of the wine is changing over time when the height of the wine is 4 feet. So when I write my equation, I will have to use the volume formula for a cone, which is 1/3 pi r squared times h. If you do not remember these geometric formulas, they are at the front of your book, but you do need to remember the volume of a cone, and some other basic ones that I will talk about in class. All right, and notice here that we have an R and an H, but we only have H equals 4. So we don't actually have the value of the radius ever. So we cannot keep our equation in terms of R. We need it to be all in terms of H. Another way that you know that you have to rewrite this in terms of only one of the two variables is that you are looking for dH dt, and you have dV dt. You do not have a dr dt. So if you were to take the derivative of this, you would have a dr dt floating around, and you don't have a number to plug in for dr dt. So we're going to go ahead and rewrite R in terms of H, using actually similar triangles. So if you notice, we have the wine barrel similar triangle. So we have 6:12. And then we also have the wine itself similar triangle, which is R:H. So I can rewrite R as H/2, because if I did 6/12, which reduces to 1/2, equals to R/H, and solved for R, I would get H/2. So I then plug in what R is, which is H/2, into my equation. So now I don't have any more R's. And I'm going to simplify this a little bit before I take the derivative. So I can square the H/2 and multiply the like terms. And so I now have that the volume is 1/12 pi h cubed. Now I can go ahead and take the derivative, keeping in mind that 1/12 times pi is just a multiple constant, so it's just going to come along for the ride, so you don't have to use the product rule. So my equation that I get after I differentiate is dV dt equals 3/12, because the 3 multiplies the 1/12, times pi h squared dH dt. I'm going to do some simplifying first so that I get the following. And I have dV dt, which is -6. I have h, which is 4. And I am looking for dH dt. So that's what I'm going to have to solve for. So I plug in what I have. do some simplifying, and solve for dH dt. And you can simplify that even more. And you can leave your answer as such. If you wanted to, you could turn that into a decimal. So my final answer is that the depth of the wine is changing at a rate of -3 over 2 pi feet per hour. All right, I want you to see if you can do this problem by yourself. Let's see how we did. Suppose that you are the supervisor of a water reservoir for King County. Further, suppose that this reservoir is in the shape of a cone that is 50 feet deep and 200 feet across. There is a drought in Washington, and the water level is falling at the rate of 0.002 feet per hour. The water level has dropped to 30 feet. It is your job to know at any particular time how fast, by volume, the reservoir is losing water. So how fast, by volume, is the reservoir losing water when the water level is 30 feet? All right, so if we have our picture of the water reservoir as the shape of a cone, we label what we are given. The height of the water reservoir is 50 feet, and the radius is 100 because the diameter is 200, because it says 200 feet across. We do not know the radius or the height of the actual water itself. We are given that the water level, which is the height, is decreasing because it's falling at a rate of -0.002. What I want to find is the rate that the volume is changing when H equals 30. So, in order for me to use my equation in terms of one variable, I will have to use the similar triangles like I did before. So that means I can rewrite R to equal 2H. So using the equation, the volume of a cone, I can rewrite it so it's all in terms of H, simplify, and then go ahead and differentiate. So after I differentiate, I get dV dt equals 4 pi h squared times dH dt. Now I'm going to plug in what I have. So I plug in the 30 for h, and I have the rate of dH dt, which is -0.002. Do some simplifying, and I find that the rate at which my volume is changing is -22.6195 feet cubed per hour. All right, the next type of related rate problem that's very common is a Pythagorean theorem problem. So this example is called the UFO problem. The TV show Unnatural Experiences and Nauseating Aliens claims to have photographed a UFO as it flies overhead at a constant altitude of 3 miles and a constant speed. They state that they took the photo, which resembles a very blurry cigar, at the instant after the UFO had already flown horizontally 4 miles past the point directly above them. They say that the radar gun showed that at the instant the photograph was taken, the distance between the photographer and the UFO was growing at a speed of 384 miles per hour. Determine the speed that the UFO was traveling. So, here is my lovely little picture of a blurry cigar UFO with a photographer at the ground. What I'm given is the height of the UFO, the altitude. It's a constant height, so that's not changing, so I can label that as 3. What is changing is the distance the UFO is to the photographer, so I'm going to label that as X. What else is changing is the length from the ground to the cigar, or to the UFO, so I'm going to label that Z. What I am given is dz dt, which is 384 miles per hour, and that's the distance between the photographer and the UFO. And it said it was growing, so it's positive. What I want to find is the speed that the UFO was traveling, which means I want to find the rate at which this distance, the horizontal distance, is changing with respect to time. Specifically when the UFO had already flown horizontally 4 miles past the photographer. So what type of equation am I going to use? The Pythagorean theorem. So I set up my Pythagorean theorem, and you can simplify it. And I can go ahead and differentiate. And when I simplify this even more, if I divide by 2, the 2's cancel. Now I have to plug in what I have. Well, I don't actually have I do have the value of x, which is 4. I do not have dx dt, so that's what I want to find. Here's what I don't have is z. I do have dz dt, but I don't have z. So in order to find z, you will have to perform the Pythagorean theorem when x equals 4. So I'm going to do that off to the side. So I have 16 plus 9 gives me 25. So z equals 5 when x equals 4. So I can go ahead and plug in 5 for z and everything else I have, and then solve for dx dt. So this tells me that the UFO is traveling at a speed of 480 miles per hour. All right, go ahead and see if you can do this problem on your own. A man on a dock is pulling in a rope fastened to the bow of a small boat. If the man's hands are 12 feet higher than the point where the rope is attached to the boat, and if he is retrieving rope at the rate of 3 feet per second, how fast is the boat approaching the dock when 20 feet of rope are out? Okay, so here is our picture. We have our boat, and we have the distance it is from the dock, and then we have the length of the rope. So what we're given is the height that the rope is from the dock, which is 12 feet, and that is, or not the height, the man's hand, sorry. And so that doesn't change. What is changing is this distance, because we're pulling in the boat, and the length of the rope is also changing. What we are given is dz dt, which is the rate at which the rope is getting pulled in. So the length of the rope is getting smaller, so it is -3 feet per second. What I want to find is how fast the boat is approaching the dock. So I want to know this rate, the rate of the distance, when the length of the rope is 20 feet. So my equation is a Pythagorean theorem, x squared plus 12 squared equals z squared. Simplify it, differentiate, I can cancel out the 2's. The one that I do not have is x, so that means I need to figure out what x is when z is 20. So after doing the Pythagorean theorem, you would get that x equals 16. Plug in everything I know, simplify. So the boat is approaching the dock at a rate of -3.75 feet per second. And if you just wanted the speed, you would just take the absolute value of this. The negative just means that the distance between the boat and the dock is decreasing. Well, I hope you enjoyed related rates, and don't worry, we will have lots of time to practice these because they are hard and they can be confusing. All right, I will see you in class tomorrow. Have a good night.